Okay, welcome to our fifth note set in the reverb section, where we're going to talk about modeling the early echoes. Again, we're drawing largely from that chapter 3 in an edited book, the chapter written by William Gardner. I've mentioned in previous videos how I think you might be able to get access to that chapter from interlibrary loan at a library near you. So we're in the last note set, we looked at kind of the general perspective of doing reverb, not convolution reverb, just coming up with some discrete time system that will mimic reverb. And so we saw that there were two parts we needed to worry about, the early echo part and the late reverb part, and they had very different characteristics. So in this note set, we're going to be focusing on the early echoes. It's just 7 slides, 6 really if you don't count the title slide. So it's pretty short because it's pretty straightforward. Although there is a bunch of magic and art in it, and I'll mention that as we get into it. And then in the last 2 note sets, we'll talk about how to do the late reverb, and those are much more complicated. Okay, so here's our simple starting point. So I have mentioned that Schroeder's papers back in 1962, I think, and 63 were the starting point of all this digital modeling of reverb. And at that point, he didn't even really focus on any early echo issues. He was just trying to model the late reverb. And then it wasn't until, 7 or 8 years later that he wrote a paper where he addressed the early echo model. So whatever goes in here is what we'll talk about in the next 2 sets of notes. We're really focusing on what goes in here to handle the early echo. So we alluded to these structures in the last note set. This is an FIR and IIR in parallel. You can see that the input goes into the FIR and into the IIR, and then you just sum them. And the idea is that delay there just makes it so that the output here doesn't start until the output here ends. So you can kind of see that you get the FIR part stops, and then the late reverb stuff from the IIR starts later. So we're using E for early and R for reverb. And we've already talked about how this is perhaps best viewed as just a very sparse FIR. And we've talked about how this, although we'll see this in much more detail in the next 2 videos, but it makes sense to have that be an IIR so we can have these echoes just recirculated over and over to create a nice dense diffuse reverb kind of environment. So that's what we've talked about, that sparseness is the fact that we don't need all the FIR taps in this FIR filter. So most of the coefficients in that are going to be 0. And then we pick the total delay through this FIR to just correspond to the length of the early response that we're trying to mimic. And like I said, the Z to the minus D is just there to align those. So this box here, we can see a representation of what it might look like down here. So these M1s and M2s and so forth, they model, well, I guess I'm getting ahead of myself. So the tap gains, A sub I, those are going to model all the reflection coefficients. And that's where the art comes in. The science doesn't tell us really what those should be, although we could go and measure the impulse response of a particular room and maybe kind of get an idea of what those things might look like. But I suspect that a lot of it is just kind of playing around with it and getting it to sound right. And obviously, we want to give the user a bunch of options and maybe have a knob that will control certain characteristics of the early model. So there might be some algorithm that would take a user's input and just randomly generate those in some appropriate way using some sort of rule. So that's the tap gains. And then we have the delays, the m sub i's. Notice that this is not a z to the minus 1, that's z to the minus m1. So in reality, there are m sub 1 unit delays cascaded. And ordinarily in the FIR, we would think about there being a tap in between each of those. That's what we mean when we say that it's sparse and that we don't need all the FIR taps. And then we have M2 and M3 and so on, however many we want. And since those things are modeling the early echo times, we really don't necessarily want those to be, multiples of each other. We certainly wouldn't want them to all be equal to each other, because that would lead to a very unnatural sounding thing where all the echoes are kind of coming in with the same spacing. So picking those again is somewhat of an art. You might want to make those things a bunch of relatively prime numbers or something like that. But what you do want is the sum of those, since the total end-to-end delay is the sum of all those m values. You want the sum of those m values to be the total desired early response duration, which is something on the order of 100 milliseconds. So given the typical sampling rates, so that's like about 22 microseconds in between each sample, can give you an idea of what this sum needs to be to get out into the region of 100 milliseconds. And then here's this R of Z at the end here. That's this R of Z here. And so with it set up this way, we don't even really need an explicit Z to the minus D. We're really just using all of those things for double duty. They play the role of the delays in there, but they also play the role of the delay that's needed here. And because nothing gets to this, to go into here until it gets all the way through here, we'll have that the reverb part does not start until the early echo part ends. So that's the idea. Okay, so that was one structure. About 9 years after that, a guy named Moore published a paper, and his paper wasn't really an academic paper. It was more of a, here's some things that I've been playing with and I tried, and it sounded good. So it was more of a practitioner's paper, I would say. So what did he do? Well, he said, let's take this FIR. We can build that just like we had before, so that the stuff coming out here will be the early delay, or I'm sorry, the early reverb, the early echoes. And then we can adjust this D1 and D2 to make sure that whatever's coming out of here will start right when the early echoes coming here end. So you can adjust the D1 and the D2 based upon orders of the FIR and the IIR and so forth. But the big difference is the signal doesn't go directly into the IIR like we saw on the previous slide. No, the thing that drives the IIR is all the early echoes. And that kind of makes sense. That's really what's happening in the real world. It's not like the actual signal goes directly into just the reflections that make the reverb. No, the thing that makes the reverb is all those early reflections continuing to bounce around. So this kind of makes sense. And we'll see later that we have a hard time getting this thing to give us the echo density and time that we need. Well, this just helps that, because instead of just having, if we're thinking about the impulse response of this path, it's no longer just the impulse response of this. It's this thing cascaded with this. So you get a bunch of delta functions coming from this, and every one of those kicks off the impulse response of that. So the actual end-to-end impulse response of that path is a sum of a bunch of different delayed versions of the impulse response of just the R of Z. And that is really nice. So that's why we say this is increasing the echo density of the late reverb. And that's really nice. So laying this out a little more explicitly, so this FIR would look like this part here. And then we have the R of Z, and we don't really need this Z to the minus. Well, yeah, they're both in there. So we would put both of those in there, and we can adjust those appropriately. So again, the tap gains model the absorption coefficients. The sum of the M's should sum up to be the total early response. I should back up. I should say that, these are really integers. So that should be equal to that times T sub S should be equal to the total early response duration. So just a little bit of a misfire there on my notes. Again, the R of Z, just like before, models the late reverb, except now it has the assist from all the spikes coming out of that. And like I said, we just adjust those other delays to make everything start and stop at the right places. And then there's this G here, and that allows us to kind of set the level of the late reverb with respect to the early reverb. And so that might be a nice user parameter to allow. Okay, so two different approaches. Now, those are very simplistic in the sense that all of the filter coefficients are just constants. And we're talking about a sparse FIR filter here. And so it turns out that this really just doesn't sound all that good. It was a good improvement from not having it at all, but it just sounds too discrete. Like you can hear these echoes and they just sound too individual. And you can especially hear that when your input is some sort of impulse-like signal. So like maybe, the clicking of drumsticks, or maybe some castanets, or something like that. Various types of percussion and so forth might sound not so good in this if we used the approaches that we saw in the previous two slides directly as they were. So to make these echoes less discrete, we'd like to kind of diffuse them a bit, spread them out. So instead of having a constant here that's just A1 and a constant here that's just A2, what we can do is put a filter in here, and what that will do is spread that out. So think about it from a delta, an impulse response point of view. If we put a delta of N in here, we were just before, when we just had a constant here, A1, we would just be getting a delta at the right location. So that would be at a location of M1 with a amplitude of A1. But now it's going through a filter here, and we know that filters are, when they get hit with a delta, will spit out their impulse response. And so now what we would get is, at this point, instead of just getting one spike at M1, we would get a sequence of spikes. And we can make those do anything that we want by choosing the impulse response of that. And then you'd get another one. So that might be further on, and we'd get a bunch of spikes due to that. And so that just makes those echoes less discrete. That's one way to think about what this is doing. Now, we also, back in the last note set, I think it was, we talked about how if we think about one single path from source to ear, it's going to hit a bunch of walls, and each wall has a frequency-dependent absorption. So we can model each wall with a frequency response. And since we're hitting wall after wall after wall, the overall frequency response of having hit so many walls is a cascade or a product of those frequency responses. And then there's going to be some losses and delays and so forth due to just the air propagation. And that might not be frequency dependent, but it might be. So we could make that. So if we use this model, we can think about this going in for that and another version for that. So for each of these filters, we might have a different version of that and a different set of those. But we can use that to guide our thinking about this. So we could sit down and think about a particular room and maybe even devise what we think these things should look like. So again, I'm not giving you enough detail that you could go out and actually start to design one of these things, just trying to give you the ideas so that if you do get into this field and you start looking at what people are doing, you'll have an idea of where those ideas come from. Okay, we could do a stereo version of this. Remember, we said that a listener has two ears and that you might get something different in the left ear and right ear for different reflections depending upon which side of the head they're coming from. So if it's coming from your right side, what you're hearing in your left ear from something coming from your right side is a little bit filtered from what you would hear in the right ear. And so that's the head-related transfer function. So one approach is we've added in these things that we just talked about on the previous slide, and then we split that into a left and a right, and each one of those can have a different left and right because we can think about each one of those reflections coming from a different direction, different angle. One could be coming from, straight behind. So all those different things can be incorporated into this. Now, the problem with this is a perfectly good view. And in fact, this is probably the most comprehensive view of what's really going on. But there's a lot going on here that we would need to nail down in a design, and we'd have to figure out how to implement all these. And we'd have to figure out how we give a user control over these so that they can, with changing a few parameters with some knobs or maybe a user interface through a GUI or something like that, they can make changes and settings that make sense and sound good. So this is a little bit of a challenge. And so we might want to think about simplifying that. And so one way that people have done this, a bunch of people have talked about this in the mid-1990s, is that instead of having every one of these different delay points have a filter and different head-related transfer functions, we simply say, well, there's going to be a subset. So maybe we've got some other ones coming along here. And maybe we'll say this one and this one. So maybe all the odd indexed ones might get summed together, and all the even indexed ones might get summed together. And then we process each sum with a head-related transfer function. So that's just a way of simplifying this. We don't need a head-related transfer function for every reflection. It's not exactly right, but it might be good enough for whatever it is that you're trying to do. Here's an even simpler approach that someone by the name of Jot with a few other people in the mid-1990s introduced. And they said, let's keep the A1s and the A2s, although we could put some filters in there too. They didn't talk about that in their paper, but there's no reason we couldn't put these as filters. That's not what they're talking about. They're talking about modeling the head related transfer function. So what they do is they talk about a delta TI. So they just delay the left with respect to the right. And they're showing that the delay is always in the right side. That leads me to believe that these deltas should also be able to be set to be positive, so that we could have the left happen before the right and the right happen before the left. I think this was maybe just a glitch in the diagram here. I think on some of these, it might make sense to be able to put this in one side or the other. But anyway, that's what those things are doing. And they're just capturing the time difference between hitting the right ear and the left ear, and how that will be different depending upon the angle at which that echo is supposed to be coming from. And then you can set using some interaural intensity differences. So we talked about these interaural time differences and interaural intensity differences in the last note set. So these things would set that as well. And so that sets a lot of the directionality. And then we just have one pair of left and right transfer functions rather than having one for each direction. So the directionality is handled here, and then this just handles kind of the muffling of a head-related transfer function. Low-pass filtering kind of idea. So that's the idea. So that is another alternative that was proposed. And then also getting into the later 1990s, a person by the name of Greisinger wrote a paper. And again, this is kind of more of a practitioner, here's how I did it kind of paper. So Greisinger is just saying, I took 6 echoes, so M1 through M6. I don't know if the paper gives you values for those M's, but you could go and look there. And then what they did, this is what I was alluding to earlier, they grouped them into odds and evens. So you can see 1, 3, and 5 all get summed together. And 2, 4, and 6 all get summed together. And then they do the interaural time difference, and you can see now they're doing one set has the delay on the left side and one set has the delay on the right side, and then whichever one gets delayed gets hit with a transfer function. And that kind of makes sense, right? It's the delayed one that's on the far side of your head, and that's the one that should have some muffling to it due to a low pass type filter. So that's what they've done here. So the interaural delay, they tell you what the delta T is that they used there, and they tell you what these low pass filters were. Just a simple one pole IIR low pass filter. With a cutoff frequency of 2 kilohertz. So again, I'm telling you, as I said, this paper was not, a theoretical paper. It was literally saying, I did this and I found it sounded pretty good. And they do tell you the M1s through the M6s arbitrarily between 10 and 80 milliseconds. That's not the values of those. That's the actual delays at these positions would be chosen arbitrarily between 10 and 80 milliseconds. So maybe you'd pick this as 10, and then the full range here would be 80, and then you'd pick these other ones to give you other values between 10 and 80 milliseconds. And then there's 2 gains that we can work with. An echo gain, G sub E, sets the level of what goes through there. And then a direct gain, there is a direct path that goes straight through to there. So that was another approach. And I would imagine that there's lots of other approaches out there. And like I said, a lot of this is art. Getting the right coefficients for A's, getting the right values for the M's, getting the right interaural delays and so forth. This paper gives some suggestions, but there's probably lots of information out there. But this should give you an idea of kind of how these early echo approaches are handled. So with that out of the way, the remaining two videos in this unit will focus on how to do the late reverb, and that's a big challenge. So in the next video, we'll look at the early approaches pioneered by Schroeder. And so that was 1962 and 1963, I think, were the years. So we'll go into detail of those papers, and then in the second remaining video, which would be the last one in this reverb unit, we'll look at a approach that was proposed much later and is still being used today. So it's a feedback delay network, and it's based upon some ideas that came out much later than Schroeder's original paper. And if you remember back, and I think it was in the very first note set on reverb, I showed a picture of a modern guitar pedal called Big Sky. I forget who actually makes it, but the name of the effect box is Big Sky. And on the web page, they talk about how they still use this feedback delay network that we'll talk about in the last note set. So I hope that we'll see you there.